Another way to make images, scientists working with their colleagues. So this is something I do often, and this is something that Travis Rector does often. Same object, different telescopes. Mine's with the Hubble Space Telescope, and I worked with Penn State astronomers. And Travis made this one of the same group for the Gemini telescope. You can see here that we chose different orientations, and indeed we chose to color our data differently. Okay, so his is quite a bit more purpley pink, and mine's a richer blue. Both of them are valid. Neither one is wrong. They're both interesting, they're both informative. This is really exciting. Taking people where they've never gone before, they're used to optical astronomy. This one here is for radio data. And here's the Dominion Radio Astrophysical Observatory Synthesis Telescope. These are my colleagues that I work with. And here's an example of an image that we made. This is the Cygnus region. Now this is also a very important point. Some people think that these tutorials are just for optical images, but they're not. There's no optical image here. There's radio continuum data and infrared data to create this image of supernova remnants like this and clouds where stars are being born. And between it's the plasma and dust and the infrared. I'm going to make little summaries as I go en route in this talk. Well, first of all, let's recall that they're meant to pique the public's interest and not describe all of the science that's possible. Remember also that they're not snapshots of what one would see truly with their eyes. Even for the David Malan images, those are more sensitive than what you would see with your eyes. You need to balance scientific information, or at least that's what we would like to do as scientists, balance the scientific information with how an image is visually comprehended by the intended audience. So how are the optical images made? Well, this is also very relevant to radio images, but I'll tell you about that in a moment. Let's start with the easiest one. We have our electromagnetic spectrum here, and here you can see how the Hubble Space Telescope actually selects specific regions of the electromagnetic spectrum. Okay, and most of the images are outside of the range that your eye would see. So generally when I'm talking to the public, I tell them about filters and how all of the electromagnetic radiation goes through a filter and then just passes a little chunk of the electromagnetic spectrum. And then it's in black and white so that it's very sensitive. That's the way that CC cameras are most sensitive, is if they don't have to also store color information. So that's why we use them that way, but we know where they are, so we could color them if we knew what the color was and if they actually had color. Now, since we only have two here in the optical, we get to select what colors we're going to do for the ultraviolet and the infrared. And we put them together, and that makes an image like this one. And you can see that there's more than 3 images here. How we assign the colors actually became an issue for the Hubble Heritage Project, or at least we were the first people to have to communicate what we were doing in a way that was consistent. If we had a filter in the ultraviolet and one in the infrared, and we colored the ultraviolet one blue, and we colored the visual one green and the infrared one red, we would call that chromatic order because it's in a kind of natural ordering of the spectrum. But sometimes we wanted to, and you can think about why, change the color of the filter and not use it in this chromatic order. And when we did that, we called it composite. So in that we might color the infrared one blue. There are other terms you might come across in reading about images, and for example, we have the natural, which is really a chromatic ordering, and usually that's used for galaxies. Those very nice pictures of, bright pictures of Saturn, representative it might be called, and that's a composite ordering where the filter colors have been assigned in a different order. And I want to emphasize that this isn't an arbitrary order. Indeed, even the very famous Eagle Nebula, right here, is an enhanced chromatic image where the colors don't match the colors of the spectrum. but it's not arbitrary. To explain how it's not arbitrary, I want to show you one example, and I brought the data in case anybody wants to work on this when we do our little workshop. But here's 6 filters from Hodge 301. And what you can see here is we have a star cluster here, here, and here, and these are the broadband filters. Okay, so those are pretty easy to color: blue, green, red. Notice that if you do look at the spectrum, this is one of the colors in that filter, but really it goes from blue to kind of yellowy, almost orange in that filter. But you can pick the middle wavelength and say, we're going to color that one green. But notice these narrowband filters here. So these narrowband filters here, this one is for oxygen, that would be green. This one is at the H-alpha wavelength, pink, red. And this one too would also be a pinkish red, okay? So if you put these two together, notice how different the black and white images are. If you colored them both red, you'd lose that differentiation and you wouldn't have the different information. Look at this beautiful structure here and this diffuse emission there. So you want to color them 2 different colors, not the real color. When I talk to the public, I tell them to be aware of a few things. NASA's Hubble Space Telescope snaps a photograph up, if you see that in the newspaper. Well, we're doing digital photography, and it's a combination of black and white data. So when you're making your images, you should make it clear that you're not making a snapshot or just a photograph. Okay? Don't let them put that in your press release. If it says this is a true color image, well, you've learned now that most of the Hubble Space Telescope images are from infrared and ultraviolet, so it's not what your eye would see. Here's an example of what your eye would see. If you look at this planetary nebula in a globular cluster, what you see is that it actually looks kind of greenish and all the stars look the same color. This is because your eye doesn't respond well to faint light. So what happens is your eye turns everything white and maybe a bit greenish. But if you go and you take a spectrum of this planetary nebula and you look and see which element is strongest, it turns out to be hydrogen. And hydrogen glows pink. So there we have a pink planetary nebula instead of a ghostly green planetary nebula. And here's another thing you see. You see blue stars and orange stars, which is true. We have hot stars that are blue and cool stars that are orangish. So this image here is the one that tells you what's true to the physical phenomenon and what's not true to your eye. This is what your eye would see, and this is what is really there. So there's a philosophical point. What should we call true color? NASA accused of false advertising. Here, as we'll see when we do the workshop, we'll do several different strategies to figure out what color we're going to color our image. And that's what they did for the Cone Nebula. So this one's mainly red in the background, and this one's mainly blue. There isn't any full spectrum, what your eye sees, filter in this image. So you could color it whatever you would like, because they're ultraviolet and infrared images there, right? So both of these are valid. It turns out that the editors liked the red one and indeed put it on very many magazine covers, and so that's the one that was selected to be the image. Let's talk a bit about retaining our scientific meaning, and that's easier to do when we're looking at radio images. Now, radio images are great because now we really don't have to care what the eye sees, right? We can assign it any color we like. Here's part of the sky. So over here there's a pinkish glow, which is due to ionized hydrogen in this optical image, thanks to Charles Dunn. Now let's look at this very same patch of sky in neutral hydrogen.